Okay, well, good morning, everyone. So here we are on the last day of this short course. And the first lecture this morning is on hybrid materials and repair with the case studies. So we'll be looking at a number of examples where DED has been used for these purposes. And as I have done with the other presentations, there's sort of a smattering of primarily powder bed fusion in here as well, because I thought the examples were particularly good. So let's talk about what hybrid additive manufacturing is. I've read a number of papers, and I've talked with people that say they're doing hybrid, but I really don't think they are. But so this is the definition. Hybrid manufacturing processes combine two or more different processes into a single fabrication mode that synergize aspects of each. So we want to basically have the two processes come together in a way that we get actually more than just the two processes. And so, again, the most common hybrid additive manufacturing process incorporates subtractive processes into the additive. And it's, again, primarily to be able to do surface finishing on surfaces that are accessible to machining during the build, but which are not accessible to machining after the build. So, for example, if a part can be additively manufactured and then taken out of the machine and machined adequately, that's really not a very good example for hybrid manufacturing. So we'll be looking at some of these. You know, these hybrid machines have been around really since the late 1990s, and the table that I had, I think maybe from the last presentation, that had all of the companies in the world that were doing DED. I made notations on that table, which ones were doing hybrid manufacturing. So anyway, so this is, I want to take a look at this. This is, hopefully this will work. We're going to go to we're going to look at some websites and see some of these, because the manufacturers actually have some very nice demonstration examples. And so the one I want to show here is the hybrid additive manufacturing machine from the Japanese company Matsuura. I think they say the machine has been developed since 2002. And I actually happened, it was about 2004, maybe 2005. I was in Japan and actually visited Matsuura and saw their machine. It was a massive, big machine that would produce metal parts that were finished. It was very nice. Let's see if I can get this movie to work here. That seemed to be pretty easy, so I think we can just play this guy. I don't really think we need the sound for this, but oh, you're not seeing what I'm seeing. So. There we go. Great. Perfect. Yeah, thanks so much. So we can just see how this works. This again, it's a powder bed machine, not a DED. But they come in every so often with a milling cutter and do the machining. Matsuura, by the way, is a humongous machining company. So they moved from machining into additive. see all of the different materials. I don't see titanium on this list, but they pretty much all the other ones they do. I think that takes us to the end of that. Let's see if I get back to where we started. Looks like this is working. Okay, and let me show you another one that's from DMG Mori. This is, I think, is another Japanese company. They're also a machining company that's gotten into the game. So let's take a look at this one and see if we can make this one go. So I just need to stop the presentation. Is that what we're doing? Okay. Okay, I think this is the one I have. Yeah, this is the one where I have to find the right one here. Let's see. Let's see, I think we're doing it this way. I think I searched for the idea. This doesn't seem to be up here. So let's see here. We can go back. If I leave, we can go back and try again here. We'll see. Yeah, the deal is they have various. These have to be hopefully. So actually, I think this one. See if I have this one. And so here you can see they have tool changers, so they're switching to the machining mode. So you can see the how this is working. So looking at this is a slide that just simply says that with machining, the more we take away, the more expensive the process is. However, whereas with additive, the more we add, the higher the cost. So that's really the gist of this slide. So I think we'll jump ahead here. Fraunhofer IPT, which is the Fraunhofer, is one of two in Aachen, Germany. They're actually separated by a driveway from each other. The other is the Fraunhofer ILT. But the Fraunhofer IPT had developed a process which you can sort of see over here. But they went out of business. But I wanted to include it anyway. It's laser welding with either powder or more commonly a wire feed. So it's really a wire-fed DED. And the materials fit in the mill pool, combining with milling of contours in the surface. And they were trying to do rapid tooling, sort of like the movie we just watched from DMG Mori that showed the finishing I think it was a die casting die. So this is the same thing. So the selling point was to reduce the need for EDM for deep slots, but they had a lot of milling difficulties and with mastering conventional tool skills. So it was on the market for about 10 years, but had problems. But the concept was very consistently hybrid manufacturing. Here's another one. This is directed energy deposition, the so-called ambit method. And it's one of a variation of hybrid manufacturing processes. Generally, what we have with hybrid, what I've observed, is that there really are sort of three different sort of variations. One is we take an additive manufacturing machine and we sort of modify it to do the subtractive, or as has been the case in the examples I've shown so far, we have a machining company that takes a machining machine and sort of adds capability for doing additive. In this case, what the ambit tool does is it's sort of a modular insert that works almost on any machine. So you take like a CNC machine, and this ambit head is just like a machine tool. It sits on the tool changer just like the other tools, and when it's time to use it, the CNC will grab it and it can do what it needs to do. Of course, it's laser based, so of course there's some safety protocols that have to be in place. So it's not just a matter of buying this attachment and sticking it on the machine, because there's lasers, so there's all these workplace safety considerations in terms of lasers in manufacturing that have to be met. But anyway, it's a nice idea. It was developed at De Montfort and MTC in the United Kingdom, and it uses this AM deposition head as one of the tools in the magazine. The laser and the material feeding system needs to be docked separately, and again, it can be fitted into most CNC machine configurations and robotic platforms, and then, like I mentioned, the machine guarding must be upgraded to a light-tight enclosure. So let's see if we can make this one work. Let's stop this. We'll go down here. Let's let this go. see. So yeah, anyway, we see some examples here. Here's the hybrid. Let's see if they have a movie here for hybrid. I think this is the way it works. But at any rate, you can tell this shows a little bit of how it goes. Again, they just have a separate head that comes off on the machining side. So I think that, let's see if there's something here. Yeah, it shows the head. I think maybe that's all we see here. They don't have a good movie to watch, I don't think so. But anyway, so that this is the way it works. So yeah, we have that separate head. So let's go back to the PowerPoint. So here's the next one is Mazak. They have a machine that's, again, strict energy deposition. It integrates the additive deposition head into a multitasking CNC machine. And so the deposition heads were developed by Hybrid Manufacturing Technologies, turnkey solution, 5-axis milling, as well as laser marking. So let's see what we can find here. So this is a kind of a, let me make this work here. This shows for their, what they can do. And again, it's where they have both a laser metal deposition machine as well as the wire arc, and so that they're comparing basically the capabilities that they have for those two. And so obviously the wire arc is a rougher surface finish, but again, they're basically useful for for doing repair and coating and microfabrication coating in near shape forming. So it's kind of a nice table. Again, this just shows there's nothing really new here in the schematic on the additive side, but you can see how they can produce the various parts within the machinery. So this is like a boss or something that's being added to a workpiece. Again, they can do this kind of thing because it's a 5-axis work platform for building parts. So anyway, so that's that. They also have wire arc. The wire arc uses a arc process to deliver the material. I think I have a couple of photographs of this coming up. But at any rate, you can see that basically they can do the usual. They lay down the metal and then back machine what needs to be machined. So anyway, so that's that. I think I have some of these to show you in the slideshow. I copied some of them so we can look at them. We can look at them here. So again, we can see how the machining head and the laser comes down. This shows their workpiece. It's the base material is an aluminum alloy, and the added material is a similar aluminum alloy. But you can see it sort of to the bottom and to the right is the as deposited part. But then after the machining takes place, everything's cleaned up. And in this case, it is a bit. I'm sensing that in this case, as was maybe the case with some of the others, it is a bit sequential. So they build the part and then they do the machining. But what preserves the hybrid nature here is that the part is chopped up and registered in terms of where it is for both machines. So we're not taking it out, putting it in another machine, and then having to align it relative to that machine's coordinate system. Everything happens all at once. So the registration for the additive part is preserved for the registration for the machining side. So okay, so here's Laser Tech. we looked at this one. This is DMG Warring. We looked at a movie. I think that was the second one we saw. But it's, you know, again, it's basically a milling head machine with an integrated laser deposition welding head. And the welding head is developed by the Fraunhofer. So it's coaxial delivery of powders to the laser's focal point. That's fairly normal. It's an easy change between the tools and the operations because it's, again, it's kind of a tool changer approach. Safe boarded systems and manufacturing envelopes. So that was my point, that, you know, you don't have to have two. And so they work with a number of materials here. Lumex is that's the first video I showed you from Matsuura. And in their case, they have a powder bed fusion machine with it's a large platform. You can see down at the bottom, I guess it's about a quarter of a meter platform, a third of a meter in terms of Z. You know, and it's it's conventional laser-based powder bed. Then every 3 to 10 layers, they come in with a milling head and mill. We saw that movie. Yeah, and again, the main purpose was to bypass having to electro discharge machine the deep slots. And again, no need for positioning between the additive and the milling operations. So that's a big deal. And it's, again, an automatic tool changing and freezing replacement of broken tools. This is the Sodix approach. Their movie's not really worth looking at. But again, it's this is another powder bed extrusion, a powder bed fusion example, where they have an integrated 3-axis high-speed milling operation, so they can produce parts that way. Again, it's every 3 to 10 layers are milled. What they're really looking for is injection molding tooling. It's by the way, I mean, if you think about polymer processing, the tooling is not nearly doesn't have to be nearly as tough and strong as is the case for molds or tooling for metal forming, right? So it's so we can get away with just sort of machining a metal and putting it in service without having to do a lot of treatments or without having to use very exotic tooling materials. So anyway, so one of the things that's noteworthy about this machine is it really is a full CNC machine. They have let's see here. So I've lost my pointer. sorry about that. Yeah. So anyway, instant. Yeah. So but it's got 16 stored tools and a tool changer, at least one of which is the additive tool. So again, we have that. A little different. This is sheet lamination. It's neither powder bed fusion nor directed energy deposition. I thought I would show it. It's sort of a prime example of sheet lamination additive manufacturing. This is ultrasonic additive manufacturing approach. This comes out of Columbus, Ohio. It's sort of a spin-off out of Ohio State University, I believe. But basically what they have is we take foil, which is shown up here. Basically, there's just these foil strips, and then this big contraption here is actually a sonotrode that rolls over the foil and solid state welds it ultrasonically onto the previous layer. And then what they do is at some point during or after the build, they come back in again with a milling head and clean everything up. And so it's a CNC contour milling to get the tolerance and surface finish. You can do dissimilar materials. Typically will join pretty well, except that this is not really a fully functionally graded approach because we're working with foils. So I can do gradation in the Z direction only, and everything else is planar, right? Because of the nature of the foil deposition. And then, as I think I may have mentioned earlier this week, it's a great, because it's a room temperature process, it's a way to produce a metal part that has a thermally sensitive equipment like electronics or sensors. Basically the way this works is they build like a cavity for the sensor and then place the sensor and then just keep building. And so it's possible to do that. Now, it's the only additive process I think that's really amenable to this kind of approach. Okay, so we can look at thermal spray. This is Hermal or Hermley. It's a metal powder application. What they do is it's a thermal spray approach. So what they do is they're blasting metal powder onto a substrate. It's a very high speed, and the powder will fuse onto the substrate. It's integrated into a 5-axis machining center, so the part can be freely rotated. You can do however many materials you want, but also they have a water-soluble filler material, so if they want to do undercuts or hollow areas, they can use that. And then once the part comes out of the machine, they basically just soak it in water and the filler goes away. So it's kind of a nice approach, which is not uncommon in additive manufacturing machines. I think this one has a maybe worth looking at here. So let's do that. Make this work. Let's see. Oh, we've already looked at this one. Let's see. Let's see if I can find where. Okay, well maybe I'm thinking about a different technology. Okay, I guess it was a different. Okay, so let's go back. Okay, so we're right here. So we're at a point now to do a shift from additive manufacturing for hybrid to repair. So I wanted to show some examples from DED repair. And so the motivation to do repair have these components. First of all, it doesn't make sense to do repair if it's not a very expensive part. If it's not an expensive part, then you can sort of throw it away and just grab a new one. But if it's an expensive part, you can see the examples here at the bottom of these expensive parts. It makes sense actually to try and refurbish the tool or the part itself by doing repair. And directed energy deposition of all of the 7 processes in additive manufacturing is by far the best suited to do this kind of process, to do repair. So we see it again, it has to be local, not widespread, minimal volume loss, and complex geometry is always part of the deal that helps. So let's just take a look at some of these. This is an atomizer. It's 4340. It's this is a low alloy steel, heat treatable, and so we can get very hard surfaces with the 4340. This shows the worn shaft. You can see the grooves here on this atomizer shaft right in here. This is the before. So then what they can do is they basically will mount this up, and they can repair them with a spray process in this case, and with a nice bond. And in their case, they use 420L stainless, which is a marked acidic stainless steel, very high scrape tech for heat treatment. And they were able to over here to refurbish the tool. So this is the kind of thing we do. So we don't throw this away. No, we basically make it reusable. Yeah, so here's various case studies on bearing surfaces. You can see these again, various stages. This shows the deposition tool, and there's machining that goes on as well. We can see from the finish for these. And again, this is from RPM Innovations in the United States, and with where they're replacing the tool steel parts with that have long lead times, so that they can do this very quickly. They're working with cobalt chrome on the wear surfaces only, and they're improving tool life by 2 to 3 times compared to the actual part lifetime by doing this. So it's not only repair, but sort of repair and enhancement of the performance of these parts. So I think we're going to do 1 or 2 more of these, and then we'll take a short break. This is from Toyota. Toyota has this die casting die. It's for their aluminum silicon 4-stroke engine. And so aluminum silicon is a very castable material. And so this is the die, it's part of the die that forms those engines. And I think what we're looking at here is really, it's like one of these features, maybe not these two, but one similar to it, where it is worn. And you can see here that they sort of like putting a cap on a tooth. They come back in and have added material and then machined it out to refurbish the die set. So this is the common theme for repair in directed energy deposition. So I think we have time. We got 1 or 2 more here. This is an interesting one. I kind of like this one. What it is it's a way to add material to the inside surfaces of a tube or a pipe. And so what they have is the head configuration is like this. It's got this big long head here, and I guess the additive section is right here at the end of this. So what they can do is they can take these things and jam it down a bore up to 57 millimeters in inside diameter, and can add material to the inside of the bore. It's kind of a nice thing. They can repair with the the material that's there, or like the previous slide, they can add wear-resistant materials to the inside to actually improve the performance. And what's shown here is a horizontal configuration, and here you can see a vertical configuration. So both will work. Again, this comes out of RPM Innovations. Okay, we can look at one more. We'll look at one more, then we'll take a short break. This shows, again, it's this atomizer shaft, another atomizer shaft. This shows the damaged one. Notice the performance. Apparently it rotates at 13,000 RPM, so it's pretty fast. So what they did is they came back in and added material. You can see that the added material covers almost the entire length of the shaft here. In the laser repair material, and then they come back and finish the machine the shaft. You can see that it's about 14, 15 inches. So 14, 7 times 5, 35, 35 centimeters. I guess about a third of a meter. If I'm doing the math right, yeah, this is a scale in inches. But anyway, you can see, we compare this to this. It's an excellent job of doing the repair, and an excellent way to save, what undoubtedly is a fairly expensive part. So I think it would be one more for fun. Yeah, this would be a good place to start. To stop. This shows some cases of doing repairs on Type 6.4. So in this case, it's a little bit different. This is not a wear problem where the part needs to be refurbished. This was sort of a manufacturing foul up where they actually purchased forgings, but the forgings came undersized. That is, this outside diameter here was too small for it to be finished machined. So what they did is they came here. You can see they're coming along here with the laser repairs that did add more material around this outer edge. You can see the material that was added here, and then finally they were able to go in with the extra material in place. They were able to do the machining to create the part that was completely in spec. So this was kind of trying to save an error in the forging operation. So again, so the laser deposited the outer lip, made it oversized, and then finally machined the part. So, okay, so with that, before we take a 10-minute break, and then we'll jump back in and finish up. So. Yeah, thanks for helping out with this. Yeah, it was. I wasn't really sure what was going on. Jump back in. I wanted to look at some case studies for additive manufacturing now. So we're sort of moving away from hybrid and repair into some case studies. And so this is an example of directed energy deposition. The plate you see on the far right is what this case study is about. It's a sprayer plate that's again made by laser-based DED stainless steel, and they designed it, built and installed the plate in less than 5 days. And it was the first AIM part printed on the USS Macon as part of the Navy's afloat additive manufacturing program. So they actually put a machine on the boat and used it to create parts. And again, it was a nice application. I talked earlier about laser shock peening, and I guess technically laser shock peening could be considered to be a hybrid technology because it is two separate processes that are being stuck together. And so I think we've talked about this pretty well, so we don't need to belabor it. But effectively, remember, it involves using a laser, a high pulse laser, to create a deformation wave. And this can be used for primarily for lowering surface residual stresses, but also, as we'll see here in a minute, can be used for finishing as well. So again, it's sort of a fatigue life and a part performance issue. This shows an example of how that works. There's a 3/16 stainless part that they show with the laser shock peening, and basically the upshot of all of this is that even depending on the angle that's presented to the laser, because the laser basically is always traveling in Z, but the surface that it hits can vary in terms of the angle. And so this shows basically, depending on the rotation of the surface being shock peened to the laser itself, that we get if we look at this blue dot, the blue triangles, we see that it's very low, and that we're able to get to reduce the surface roughness of the part really at all angles. And over here, sort of the upshot of this is that in some cases we're able to reduce the surface finish. to improve the surface finish by doing the laser shock peening. So, so again, I guess to move towards a summary of where we're at, then what we have is we have the hybrid processes. It's typically additive manufacturing plus machining, because that's where the real value comes in. But it can be other things. You know, the shock peening would be an example of that. The best value of hybrid is when it's necessary to do the subtractive processing during the build. That fits to justify the use of a hybrid type machine. And then, of course, the DED, as we well know, is well suited for part repair. So we can use it, you know, in that capacity in a wide variety of materials and a wide variety of part applications to do repair. So I think it's a very important part of the additive manufacturing technology base that we have. So having said that, I was asked to say a little bit about myself. So we're going to switch here. We're going to switch gears for a little bit. I don't think we're going to have 30 minutes worth of me talking about myself, but I do have a little bit. I do have a little bit of material to show here. So I started my career at Texas in 1979. Those of you who have maybe graduate students, what you have to appreciate is in 1979 it was possible to be a graduate student one day and then to be a professor the next day. What we do, certainly in Texas, is it's really required to go off and do a postdoc, or in some cases maybe multiple postdocs or experiences. But that wasn't the case in 1979. So I finished at Stanford in June, and in August I started in Texas as a new assistant professor. So, and I'd like to think that they got their money's worth out of me, but anyway, I spent, basically the point of this is to say that I spent my entire career in the mechanical engineering department at the University of Texas. So I didn't jump jobs. I was very happy to be where I was. I had made a deal with my wife. We had been married when I graduated with my PhD. We had been married for 4 years, and we were in California. And I promised her that if we could go to California, I could do my graduate studies. I promised I would come back to Texas and stay there. So I made good on my on the agreement, on the contract. So here's some photos of me back when I first started in Texas. This was right before I graduated from Stanford, right before my PhD. This was actually, it's 1987. It was about the time I got into additive manufacturing. So that's where I was. And so this is the sort of the story of additive manufacturing at the University of Texas. It was in this 1986 to 1988 time frame that a student, who was a master's student at Texas, Carl Decker, he invented laser sintering. The original patent on laser sintering technology was just him. He was the sole author on the patent, so there were no other professors or anything on that. And I mentioned that at least based on the royalty stream for laser sintering, I was consider myself a 10% inventor. I really didn't do anything with the hardware, but I did a lot of the early materials work for laser sintering. And so in fact, actually it was in '87 that Carl came to my office and said, he was having materials issues with a manufacturing process. And so I said, okay, fine, I'll help out. I'm glad I did. I sort of had this sort of nightmarish vision of what would happen if I'd done like many of my colleagues do and just sort of said, no, I'm too busy, go away. Who knows what would have happened then. But anyway, it was in 1988 that Joe Beeman, another faculty member at Texas, who was Carl's master's supervisor, formed this laboratory for freeform fabrication. It was formed in 1988. I took over as the director of the center in 2007 and ran it till 2020, so for about 13 years. And then in 2020, it converted to the Center for Additive Manufacturing, Design, and Innovation. I think we've talked about that already. So anyway, so I guess, you know, for me, when I think of the main achievements, so one, of course, was producing this first metal part. It was a copper. Basically, we dealt with copper tin and lead tin solders to produce this part. It was about 10 centimeters across, and we did this in 1990 was when we published the work, and it was, but really by a long shot, the first direct metal part made by modern additive manufacturing. Well, we talked about balling. I think I could skip over this one. We've already been down this road. That balling we also saw first observed in Maine in our lab. I show here the first page of the first materials patent for modern additive manufacturing. You can see the names. I was the lead author. Harris Marcus, Joel Barlow, and Joe Beeman are all professors. And then Carl Deckard, of course, was the inventor of the process. And what we did is we had developed the rationale for using multiple material systems in selective laser sintering. It's sort of the you read the pad. It was basically something to kind of melt and glue the parts together, the powder together, and then the feedstock itself. So we use this for a variety of applications. The metal work that we did was based on this. I'll show you some ceramic work that we did that was also based on this concept. So this is the first article on additive manufacturing published in the Materials Journal, TMS. It was published in JOM in 1990, and it's a little bit of a high type article. You see the title, From Computer to Component in 15 Minutes. Well, we're not quite there yet, but anyway, it's the integrated manufacturing of three-dimensional objects. So, and again, this was, I was the last author on this paper, but again, it was this group of 4 faculty. 3 of us were materials people. Joe was kind of the machine builder, as it were. They put this article together. And so we've talked about the SFF Symposium. Again, several from this university have attended in the past. It's a meeting that's held in Austin every year. And to speak about the conference itself, it's the oldest continuously running annual topical research conference on additive in the world. And these days, there probably are maybe 40 conferences like this that have varying degrees of academic intensity that one could go to around the world. But we're the oldest one. It predates the oldest additive manufacturing journal by 5 years. So if you really want to know what what was going on, like right back at the very beginning, right at the Big Bang, then this is probably the best source. There is no other source. Again, if you remember that additive manufacturing, depending on where you put the stake in the ground, additive, typically, I say it started around 1987 when Chuck Hull commercialized the first SLA machine. So we're talking, this conference started in 1990, just 3 years after that. And so it captures a lot of the really early work. There's 4,300 presentations made. That's I don't think that includes 2024, so that's up a little bit. 3,100 papers published in the proceedings, which comprises 27,000 pages of additive manufacturing research findings. And I would, there were, the 2023 meeting, there were 589 attendees. I think that 2024 we had about the same number. And I would also rush on to say that the proceedings articles are available for free download on the site. All 30 years of it. And I think maybe I can. Let's see if I can make this work. Let's go just to show you. You go. This is the web page for the conference. The next meeting is August 10th through the 12th. Everyone's welcome to attend. Come to Austin. It's very hot, but we have a nice meeting. Let's see. I was looking for the archive here. The proceedings. Let's see. If you just come up here to proceedings archive, it jumps down here. And so what we have is all from 1990 to 2024. We have all the proceedings. It's not particularly searchable, but basically what our thinking is that you're off doing your research. You find an article that looks interesting, so you have the citation, but you want to look at the article. So basically, if you have the citation, you know the year number. So what we could do is we could pop in to that year, and then like 2001, and then you see here's the list of the table of contents. So we can grab a Suman Das article here. I just click on it, and it pops open the article. So here it is. Instead of this, the full article, you can do a save as and download it. Just free access. So it's the entire SFF conference proceedings. So if you find any article and add it in that says SFF, you know that you can go to the website and download it at no cost. Okay, so anyway, I was a member of the organizing committee in 1990. Harris Marcus, who's sadly now deceased, was the first chair. He was the chair from 1990 till 1994 when he retired from the university and left, and that was when I took over, and I did it until I retired in 2022. So, anyways, that's the conference. In the conference proceedings, the very first article in the proceedings was one that I wrote again with my faculty colleagues that were really involved with laser centering back in the late 1980s. And again, it's simply we call the technology solid freeform fabrication. Now it's 3D printing or additive manufacturing. It's the same thing, but and the conference, it turns out, we called the conference the SFF Symposium, and I can tell you, in 2009, we had quite a quandary because ASTM had established the quote official standard name for the technology as additive manufacturing. And so I wasn't sure. It's like, well, what do we do? By 2009, we'd been running this meeting for almost 20 years. And we had a pretty good brand name for the meeting. And so we really didn't want to change the name, but we also wanted to, we wanted to be modern and up to date and accurate. So I actually had a long conversation with our scientific committee. We have a scientific committee separate from the organizing committee. And I asked their advice, and what we came up with was to sort of shorten the name to the SFF Symposium, which is what everybody called it. And we're not going to really associate solid freeform fabrication with it. But then we add on as a sort of an afterthought that it's an additive manufacturing conference. So the official name now is like the Annual International SFF Symposium, an Additive Manufacturing Conference. So it's kind of a long name, which sort of captures all of the different pieces. Okay, the first part that we made in 1990 was this copper. Well, it really wasn't a commercial metal, but in 1996 or so, 1999, and I guess we've already been over this part too earlier. Suman Das, who's the first author of this paper, did the work. He actually designed and built this high-temperature workstation that had a powerful laser. It was able to heat up to 800 or 900 degrees centigrade, the work chamber, and we were able to produce some really nice parts here. So this is fully dense titanium 6.4. This was done again 1999, which is about 3 or 4 years before the first quote commercial metal machine really hit the market, which was a European machine. I spent a lot of time talking about F-42, the Standards Committee. I was involved by, it turns out that in the fall of 2008, there was a 15-person team that was met. It was put together by Brent Stucker, who is, where is he now? I can't remember where he is now, but he started, I will rehearse his whole career. He wound up at ANSYS because he was doing, he had developed a company, 3D Sim, to do modeling of additive manufacturing. It was kind of a nice program. It basically, you sort of input the machine parameters and it output for only for titanium, Ti-64, it output what the microstructure and properties would be. So it's kind of a nice program. ANSYS bought him out. He moved to ANSYS. Then he wound up at working for ASTM. He may be at 3D Systems now. But at any rate, he was at this time he was involved with the American Society of Manufacturing Engineers, and they had a rapid prototyping committee that he was involved with, and they basically said, look, it's SME is a fairly applied organization, right? It's not a bunch of scientists; it's a bunch of users. And so they said, look, we have a demand for standards in additive manufacturing. So Brent was charged to sort of search around and see what was out there. And he came back and reported and said, really, ASTM is really where we need to be in terms of what we want. And so he went to ASTM. I showed the headquarters here. It's just north of Philadelphia in Pennsylvania in the U.S. And he basically said, how do we make standards with using ASTM? So the director of the facility, a guy named Pat Piccirillo, said, well, what we need to do is we need to have sort of a constitutional convention here. We need to plan a constitutional convention. So we need to get some people together in the field and talk about how can we organize a meeting of a bunch of people and have an agenda that will allow us to move forward with organizing a technical committee within ASTM. Once that's done, then we'll be empowered to start writing standards. So anyway, I was part of that in the fall of 2008, and we assembled the Constitutional Convention in January, I think it was around the 10th or 11th, in 2009, also at ASTM headquarters. And we, after a couple of days of meetings, it was, again, about a little over 100 people there, we actually voted to form ASTM Committee F-42. And so that's when the term additive manufacturing actually became the quote, official standard term for the technology. Again, we talked a little bit about that earlier this week. Anyway, also, I've also mentioned since 2014, I've been on the terminology committee, which again is sort of in charge of the dictionary of additive manufacturing. So if you don't like a definition of something, it's my fault, I guess. But I think we've done pretty well overall. Did I tell you the story about I don't think I told you about plasmoidy. Said for those of you that grapple with language, I probably mentioned this. Plasmoidy is worked at Syntec for many years. He was and still is the chair of this committee for doing terminology. These joint committees have to have a home either at ASTM or ISO, and this committee's home is in ISO. And so Klaus convenes this group. We were doing Zoom meetings, years before COVID, to make this work because we had representatives from Asia, from the United States, from Europe, all there. We're all part of this because we had to make sure we covered the world. And so the problem with the committee is that we're a bunch of engineers, and our language skills are, I don't know how it works in India, but in the U.S., typically if you're strong in mathematics, your language skills are not very good. And so we would often, as we were writing these definitions, have problems with how with how the language, what the language and what the grammar should be. So yeah, again, by the way, this standard has, I don't know, I think it's like 130 or so definitions now. They're all related to additive. So anyway, so the way the story goes is we were in one of these Zoom meetings, and we had this quandary over how to make the language work. And so Klaus, who is from Sweden, said he sort of stopped the group and said, "Why don't we table this to the next meeting? And in the meantime, I will ask my mother." And then he went on to explain that his mother in Sweden was actually taught English. She taught language in their school system, and she was an English teacher. She taught English, so actually her grammar skills were very good, perhaps better than a normal English speaker. And so he did that, and she gave the answer. So we had the answer back in the next meeting, so we could continue to do our work. But then from that point on, even to today, whenever there's any language problem, someone will always say, "Plus, go ask your mother." And so we have her as almost a unofficial member of the committee to help guide us with the language. There was I didn't really mention, I don't think I really mentioned this directly, but there's a paper that I put together that I consider to be really a masterwork of materials for additive manufacturing. It's this, it was published in the SERP Annals. They do these massive review articles, and this one is on materials for additive manufacturing. You can see it's 23 journal pages long, 346 references, and it's at least as of a year or two ago, had received over 1,300 citations. The author list is really, for the most part, kind of a who's who of additive manufacturing. I was the lead author. Jean-Pierre Kruth at KU Leuven is very well known, now retired. I consider his claim to fame is that he was one of the founders of Materialize, which many of you may know. Materialize is a company that really did a fantastic thing back in the early days, I think it must have been in the 90s. The problem, what it did is they developed their magic software, which really was, it was like a cure for COVID. I mean, it was absolutely unbelievable technology, because what it could do is you could basically create an STL file, and it turns out in the old days, maybe even today, it turns out that for the program to work, every single node in the tessellated surface has to be continuous and can't overlap with itself. So we're talking millions of points to point data that one in the wrong place can kill the build. And what Stratasys did is was able to sweep through these solid models and locate and repair those errors. Before that, we were just sort of hoping and praying that the STL file would run. But after Magix, it's we don't even think of it anymore. You just run it through Magix and off you go. Well, anyway, that's Jean-Pierre Kruth. Ming Liu is a professor at Missouri University of Science and Technology. He was I consider his claim to fame is he did this sort of ice additive manufacturing where you could build ice articles. So what he did is instead of heating the chamber for the build, it's sort of an extrusion machine, but he would extrude water, and the chamber was frozen, so the water would come out of the nozzle and then would instantly freeze. And so you could build these ice works, as it were. And you might think, okay, well, what you do, you make ice sculptures, right? And they do. But it turns out they could also create, the main purpose of doing this was to create patterns for casting. So what you can do is you can create an ice pattern and then, fairly quickly create the mold cavity and then just melt the ice out and you're done. So, that's Ming. Gideon Levy is now also long retired now. He was, the most popular feedstock in additive manufacturing today is nylon. And his group when he was at the company, I'm trying to think what the name of it is. It's in Switzerland. But anyway, he was working for St. Gallen's, University of St. Gallen's, I guess. But they had an industrial side entity, which I can't remember the name of. But he actually, it was his group that actually developed nylon for additive manufacturing. And then David Rosen, maybe some of you know David Rosen, Georgia Tech professor, did a lot of work with stereolithography. Retired now and is working for A-Star in Singapore. But then I also added Allison and Adam Clear. Allison Beasley, both of these are young junior assistant professors, at least they were at the time. Allison is at Penn State University and is really a very well-known metal expert. Adam Clear was, when we did this work, when we wrote the paper, he was at the University of Nottingham in the UK. They have a humongous, large additive group there. But he's now moved to Canada, is on the backland, I think maybe University of Waterloo, where he's moved to. But anyway, it's quite a prestigious group of people. I've actually talked with Adam. He's not coming to the SFF this year because his wife is having a child at that time, which is certainly an allowable excuse. But I guess while on the subject of children and the SFF, Allison Beasley, we give so-called FAME awards, Freeform and Additive Manufacturing Excellence awards. We give a junior award and a senior award every year at the meeting. And of the senior faculty here, of the senior investigators, all of us have won that award. Both of these junior faculty have won the junior award for FAME. But Allison had a problem in August. She had just had her first child, and the child was, I think, maybe 4 months old, 5 months old, and so she wanted to come, but was concerned about her child. So I actually sort of sweet-talked my daughter, who was a mother herself, late 30s at the time. I said, "Look, will you come babysit this kid, just a few times, so she can come to the meeting?" And my daughter was willing to do that. She owes me favors anyway, so she was willing to do it. So she actually came, like for the awards banquet and some of the other events. My daughter came and sort of did child care for Allison's kids. So I was very happy with that. Okay, I mentioned that the materials handbook is this encyclopedia of materials knowledge, primarily for users of the technology. And they just in 2020, so 5 years ago, they came out with the first of 2 volumes on additive manufacturing. It's volume 24 and volume 24A. 24A is sort of design and applications primarily for metals, whereas volume 24 is sort of a general overview of the technology. But I and Terry Rollers wrote the introduction for the 2020 issue. It was an absolute pleasure to do that. I've had the opportunities on many occasions to work with Terry. He's a fine gentleman and an excellent co-author. I also, with Terry, wrote this history of additive manufacturing, which is largely what I think we discussed at the first session here of this week. But if you want to know all the nitty-gritty details about the history, it was me and Joe and Terry put this together, and so you can see some familiar graphics from that. And there's quite a bit that I didn't really talk about here in the interest of time. So this is within the Materials Society. It's the Mining, Metals, and Materials Society. It's centered in Pennsylvania. It's an international organization. We meet twice a year. But and again, I mentioned it was a 13,000 member society. Just this year, in last March, I was successful in becoming the board of directors slate nomination for the what's called the presidential cycle rotation. So if everything goes according to plan, in March of next year in San Diego, I will become vice president of the society for 1 year, and then following that, president of the society for 1 year. Following that, past president of the society for 1 year. So it's a 3-year term of service, but it is something that I'm very excited about and really looking forward to doing it. So because I think it's an outstanding society. I was on the board of directors in the right before and during COVID, and we'll skip past these things. The other thing I think that's noteworthy is I was elected a fellow of the society in 2011. This is the fellow. Most societies, ASME, IEEE, all have fellow designations, ASM International. But TMS is a little unique in that they limit the total number of fellows at any time to only 100 people. So it sort of makes it kind of a prestigious elite group. So I'm very proud to be part of that. So here's the last slide. It's some other recognition. I was really kind of happy, and just last September, there's a conference called the Laser Assisted Net Engineering Conference. It meets I think maybe every 3rd year in Bavaria, and their career award they call the Night of Laser Technology. It's kind of a fun thing because they actually have a knighting ceremony for the recipient. And so what we see here is this is Rainer Papabe, who runs the Fraunhofer, the IPT that that had put together the failed hybrid machine back in the early days. Yeah, he's actually running that Fraunhofer now. So he was the dubber. So there's a little sword here. So I was down on one day, just like in the movies, and we had that dubbing. And the other fun part about it is next year, I guess I meet every other year, next year when the conference meets again, my job as the immediate task recipient is to do the knighting for whoever the next person is. So we'll pass it that way. So I'm excited about that too. I've received a couple of Lifetime Achievement Awards. ASTM gave me one. Singapore University of Science and Technology gave me one. And I think there was one other one in here somewhere. But anyway, so we have those. The Reinhardt Award 2022 was for contributions in the realms of terminology and standardization. So it turns out that Cosmovic and I both won that award that year for our contributions in standards. Got the Sargent Award. It's a Outstanding Manufacturing Award from SME. The FABE Award I already mentioned. And down here back in the early days, I actually had a von Humboldt Foundation Fellowship. Von Humboldt, if you're familiar with the U.S. Fulbrights, the Fulbright is designed for scholars, to pay scholars in the United States to go abroad and to study. The von Humboldt in Germany is kind of the backwards version of that. They pay foreign scientists to come to Germany to study and to do research. So I was able to get one of those. So I spent a year in Germany with my family. We were at this powder metallurgy laboratory. The Max Planck Institutes, if you're not familiar with those, if you're familiar with the German Fraunhofers, they're just like the Fraunhofers, except they're more science-based and not so applied. If you're not familiar with the Fraunhofers, it turns out Germany has about 30 or 35 of these Max Planck Institutes, each of which has a theme. This one was powdered materials. And so I was actually there working. It was like a research lab type situation, type setting in Stuttgart, down in the Black Forest in southwestern Germany. So, and then the first STAR award I got was in 1986. Again, it was a year before I started being additive. So it's a really long time ago. ASM has this outstanding teaching award for young faculty, and I actually won it. It's called the Bradley Stock Award for young teachers of metallurgy. Certainly I was young back then, but not anymore. So, okay. So anyway, so that's basically me. We got about 5 minutes left, and I think I'm at the end of my. Yes, I'm at the end of my show here. So I guess we're in a position where we take a little bit of time and have some questions before we take a 15-minute break and have tea. So if there anything about hybrid or repair you'd like to talk about?
Any queries from the participants? Can we take in the tea break?
Yeah.
Are we working on metal composites as of now?
Where are we working on metal
Composites.
composites? Oh, have I or where is there work? Yeah, I have not worked on metal composites. Certainly, there is a small slice of materials that is composites, and I can tell you that the composite work in additive is typically chalk fiber or particulate composites. Largely, there's I think one machine that somehow can manage to do continuous fiber in additive. I'm not sure how it works, but obviously, it's a matter. These are powder-based processes. It's a matter of mixing the powder together. I think I've seen some aluminum silicon carbide. That's a standard metal matrix composite. I think I've seen some aluminum silicon carbide work, but again, it's it's not widespread, but it is out there. You should be able to find it. Yeah. Right. Yeah, it's a good question.
Yeah, we can have a tea break and then.
Okay, sounds great. Yeah, let's go have some tea.
Yeah, thank you.
Great, I'll see you. 11:45. We'll meet back for the future, where everything's headed. Start at 11:45. So yeah, so let's jump in. The last presentation I wanted to give you is really sort of what does the future outlook like? The future outlook for additive and directed energy deposition specifically. But what I want to do is really kind of focus on what has been reported in the most recent Wohler's report. I think it gives a good view of what the future looks like, sort of from a commercial perspective. Because I've discovered over the years that the future in technology depends on whether you're talking to an academic, like at a university, or if you're talking to companies. Because for companies, the future is a very short timeline. For universities, it's a very long timeline. So a lot of things that are almost old hat at the university in terms of development can actually be very exciting in industry when it finally transfers, or if it's on the way. So basically, the universities tend to be ahead of industry. That's just the nature of the beast. So, and because as well, the universities, we're not burdened by having to make a profit, so we can think about things like flying cars and all more wild-eyed type inventions, and we can pursue those, in discovery without having to worry about the price tag so much. Whereas in industry, that's not the case. But so this is going to be kind of an industrial perspective on what the future is. So I just wanted to remind you, I showed this at the first presentation, that according to the Wohler's report, that additive manufacturing is going to be around, it's going to grow. By this forecast, again, we're talking about maybe a five-fold increase in the value of the technology over the next 8 or 10 years. So the question is, okay, so where's the future at? Well, according to Wohler's, there are 5 areas where he believes that we're going to really see developments in additive in the future. One is the blossoming of Asia, which I think is rather exciting. The second is artificial intelligence. I talked a little bit about that as a spoiler. Food printing and pharmaceuticals is another area where there's been kind of a resurgence in additive manufacturing. Speeding up AM processing for the obvious reasons, to be able to produce parts more cheaply is the primary driver. And we'll talk and look at some advances that are sort of being developed in that direction. And then finally, I want to talk about environmental aspects, because that's an area that is increasingly important. So here we go. Let's jump right in. Asia is the prediction is that Asia is going to increase its footprint. The example that's given is well, just to jump. I'll work my way down to it. So China is going to continue to gain traction, competitive products and services. Organizations in the AIM business are advised to keep an eye on China. China, for a number of years, I would get to China at least once a year somewhere. I've been over most of the country, and my observation is that at the research level in additive manufacturing, that China is relative to the U.S. is in a catch-up mode, but they're actually starting to produce research results that are actually on a par with what we see other parts of the world, and I think that's encouraging, I guess, and exciting. There are a number of additive manufacturing companies in the country. Farsoon, I guess, being one example. So I think that's an area that we'll be watching to see how that goes. Nikon in Japan acquired SLM Solutions in Morph 3D, which got a lot of attention around the world from the commercial perspective. So Japan's kind of an interesting place, because I told you that Japan claims to have invented, some in Japan claim that Japan was where additive manufacturing was invented, on the strength of a publication on stereolithography that was produced in like 1981, well before 3D Systems was formed to actually commercialize it. But what happened with Japan is there was sort of this growth in additive manufacturing until the mid-90s, late 90s, and then it sort of dropped off, and it was almost like they got completely out of the game. So it's sort of heartening to see that Japan's sort of getting back into the additive manufacturing marketplace. So and these acquisitions are quite significant. They also show Singapore and Changi Airport. If you ever get an opportunity to fly into Singapore, plan to spend 3 or 4 hours at the airport. It's an absolutely unbelievable place. For many years, it wins the Best Airport in the World award. And they have this humongous shopping area that's adjacent to the airport, so you can walk to it. And they have lots of high-end shops. The Tiffany's in the mall at Changi Airport has this exterior produced using additive construction. They use recycled plastic from old fishing nets as the feedstock. I think it was kind of a neat application of additive manufacturing in construction, but also is sort of a nod to the development of additive manufacturing in Asia. The second area was artificial intelligence. Basically, artificial intelligence currently can convert text descriptions into striking 2D images, and there's some technologies available. Like, for example, this shoe was created using text commands to Midjourney. There's other 2D AI software such as DALL-E that can do this type of conversions. So here's another example. This is an example. Luma AI software is 2023 software. It's capable of creating crude 3D objects. So I gave you the example where someone could give a voice command make me a chair in the shape of a banana or in the spirit of a banana. And this is what pops out. And so to be able to facilitate doing the design of the printable part is one area where AI can really, I think, make big headway in terms of making it easier. The same way it makes it easier for us to do 2D objects as it moves into the 3D world. I think that there will be a great benefit, I think, for everyone. There's another approach that's out there. There's a group at MIT that's developing a technique to generate 3D images from AI-generated 2D images. So in this case, it's sort of reminiscent of the old Willemets photo lab in Paris from 150 years ago, where he was taking 2D images and sort of manually stitching them together to create 3D images, sculptures in that case. In this case, I'm not familiar with exactly the method that they're using, but again, it's a mode for taking two-dimensional data and then somehow stitching it together to create a 3D object. And here's another example of that shows in this case they asked the instructions were to create a teapot that was sort of bio-inspired. And so this is what pops out on the right side. So yeah, so these are the kinds of things that we can do. Again, what it does is simply makes it easier for someone that's not an expert in CAD or solid modeling to be able to get something that is useful. That's what they want. So I think that's a great thing. Food printing. Oh, I can't remember if I mentioned it, but with that artificial intelligence, the technical advance that artificial intelligence can do is, most additive manufacturing processes have, if you really counted all of the possible variables, there may be 75 or 100. And what we do today is we pick out the 3 or 4 most important, like the energy, power, the scan speed, the scan spacing, and the layer thickness, and we sort of just work with those. But artificial intelligence can, once the database gets big enough for it to pull from, it should be able to go in and theoretically optimize all 75 or 100 parameters in order to get an output that's desirable, be it optimum mechanical properties or optimum surface finish or whatever. So that's another more technical use of AI. Okay, food printing. Frankly, I was a little surprised about food printing coming back. This is really sort of a reincarnation of the technology because food printing has been around for a long time. I quote Hub Lipson at Cornell, who did a lot of work with food printing in 1999 or so. But he was working primarily with things like cookie dough and extrusion, where it was basically his area of expertise. But also over the years, we've seen a number of food printers that have been developed. For example, if we're doing sugar or if we're doing chocolate, the chocolate food printers I think were quite popular at one point. But what we see now is that there's this new commercial interest in producing meat and fish products, and I'm not 100% sure what the customer base is for these food products. Again, but according to Wohlers, the market remains as a niche, high-value-added products with corresponding price tags. So I assume these are fairly expensive. What's shown here is sort of a salmon-looking fillet, but it's actually printed by Revo Foods. So it's a mixture of algae, pea protein, and mycoprotein. And I'm not sure what those are, but the only example that I'm aware of for an application for this was in Germany some years ago, where I thought it was quite humane, but they were doing food printing like this, but it was for accident victims or elderly people that have trouble with swallowing. And so basically they have to eat food that's fairly well pureed. But what this does is it sort of restores a little bit of dignity to the activity because this is certainly, something like this is certainly much more attractive to look at on your plate than just say a pile of mush that would be there. So at any rate, we have those. And the deal is, if you look there, there's a half dozen companies that are out there now doing this. So there's got to be, I'm assuming there's some kind of profit margin in this technology for doing food. This is something that's sort of newly developed and is also continuing to develop. So, okay, pharmaceuticals is basically, it's making pills is the additive technology, and it's kind of like a traditional compounding lab, which I'm not sure if we have these in India, but in the United States, I would say probably 99% of all the medications that are out there we get from any number of pharmacies, and they're sort of prepackaged in certain amounts, and you sort of take what the pharmaceutical company has manufactured. That works, I think, fairly well for a lot of cases. However, we also, in Austin, I'm actually aware of one that's only maybe 5 or 6 kilometers from my house, a so-called compounding lab, where what they do is they have the individual components that go into various medicines. What they do is they actually sort of hand make the pills with exactly what the patient needs, and so it's a customized pill making, and I'm sure it's very expensive to be able to do that. But what these companies are all doing, again, there's about a dozen of these companies that are basically working with additive manufacturing. So we would think of it perhaps as a multiple material printing operation, where it's like a little bit of this and a little bit of that goes into a formulation for a pill. And at the end, they're tailored products with perhaps with modulated release profiles, so that again the patient can get exactly what they need. And again, I'm not sure, like the food processing. As I stand here, I'm assuming that there's a good business model to be made to go with so many companies in the game. But unfortunately, I'm not able to tell you what that is because I don't know where the cost drivers are. The next area to talk about is speeding up the process. We've talked about this. There are a variety of ways to do it. Again, this is all predicated on the fact that the machines for doing particularly metal processing are extremely expensive, and they build at very slow rates. And so we can actually drive the cost of our parts down if we can build more parts in a given amount of time. So there are a number of approaches to doing this. There's things like multi-jet fusion. Again, moves to consolidating an entire layer all at once rather than using a raster scan, and that results in an impressive compression of the time required to build a part. Carbon 3D split machine is the same thing. It's a micromirror array, flashing light at the specific locations underneath a vat polymerization machine. For the parts can be manufactured very quickly that way as well. And then there's also these other approaches. For example, automated design for additive manufacturing. There are several companies that are sort of helping to facilitate the design of parts for specific applications. So There's a couple that are doing internal cooling channels. Siemens has software as well for doing design to facilitate and accelerate that part of the process. There's multiple print heads. These have been around for some time, but we have, again, it's a way to accelerate the build. Rapid change modules. Again, these also have been around for a while. This is basically where you, for example, you do directed energy deposition. Then you have basically a rapid change module where you can take the part and pull it off the out of the machine, put it in a new platform, and start building again. So it's sort of a quick change kind of approach. With powder bed fusion, they have certain machines where you can pull the entire build volume out of the chamber, slide in a new one, load up the powder beds, and be ready to go very quickly. So these again are ways to try to accelerate the process. And then there are approaches for eliminating or minimizing the amount of pre-processing or post-processing that has to happen. So all of these are geared towards getting parts out the door more quickly. All right, I think the last topic that I'd like to talk about are environmental issues. I want to start off just by sort of advertising the AM Green Trade Association, AMGTA, as it were. This is a technology where, it's an organization. I listed the website. It was founded in 2019, has 60 corporate members, and as you might imagine, its purpose is to deal with environmental aspects of additive manufacturing. And so their mission is to promote and elevate the conversation around additive manufacturing, additive practices, and they have a four-pronged activity list. First, to educate the additive manufacturing sector, the broader manufacturing industry, and the broader manufacturing industry about the positive environmental benefits of additive, to promote and adopt additive as an alternative to traditional manufacturing, to develop best practices for additive manufacturing, and to help the organization's members grow their businesses and acquire new customers. So there is within ISO and ASTM, there are subcommittees working with environmental issues in additive manufacturing. And I believe there is one standard that has come out based on that work. And it has to do with the air quality around material extrusion printers. So you may have had the opportunity to go to visit labs where there are a bank of material extrusion printers, maybe 15 or 20 that are operating. And when you walk in the door, there's this automatic sort of stench of molten burning plastic that's part of it's just the nature of the beast when you have a lot of machines in a constrained area. And so basically what my environmental friends tell me is if you can smell it, that means there's something in the air that's a potential pollutant. And so what the standard does is it talks about the practice and how to control the environment so that it's safe for humans to work in. And so we'll be seeing more of those as we go. And again, this is all tied in with this organization's activities. All right. Well, we have really, when we think about sustainability or environmental effects, there really are three criteria that we think about. One is obviously the one that perhaps is most popular is to talk about saving energy. We want to use less energy to complete our whatever it is we're doing, whether it's manufacturing or forming feedstock or whatever it is. So we'd like to use less energy. There's also a carbon footprint, which is the CO2 emissions that are associated with with the process, whatever it is we're doing, whether it's creating feedstock or doing a manufacturing operation. So these, and it turns out that these two, the first two, are actually kind of connected to each other. I'll talk about that more, but the way it's connected is that most of the energy that's consumed in manufacturing comes from the energy that's necessary, the creation of the energy that's necessary to do the operation. And that energy often comes from fossil fuels. So it's the conversion of the fossil fuel that releases CO2 into the atmosphere, and it causes creates the carbon footprint. So again, I'll give some examples about that. We'll talk about it some more. But anyway, the third one is kind of independent. That's water consumption. You know, water is in many parts of the world is a precious commodity, and so the water usage in manufacturing also becomes a criterion for dealing with issues of sustainability. Okay, so let's talk about the relationship between embodied energy and carbon footprint. So what this is a plot. It comes from the ANSYS Granta EduPad system. It's actually a really nice piece of software, but unfortunately kind of expensive. But anyway, what I show here is on the y-axis is the carbon footprint. That is, how many kilograms of CO2 are created per kilogram of material. And so this is for forming feedstock. So it's not manufacturing processes. So each one of these 4,100 materials it's a material. And so they calculate they determine the average CO2 footprint, as well as the embodied energy, how many megajoules are required to create a kilogram of material. And you see the correlation is extremely strong, and it has to do with the fact that it's the embodied energy, or it's the energy that we need to create material that's creating the carbon footprint. So this is simply a demonstration of that fact. So now, having said that, it's a little more complicated because it really depends. The relationship between the embodied energy and the carbon footprint really depends on where the energy is consumed. Now, I'll give you some examples of that. So for the first one is Texas. In Texas, our energy sources are 50% natural gas, 20% coal, 20% renewables, and 10% nuclear. So basically, it's the first two of these, which comprises 70% of our energy consumption in Texas, is going to be generating a carbon footprint, because we're going to be burning fossil fuels to get the energy. Norway, as a sort of an extreme opposite example, has 98% renewable. It's virtually all hydroelectric. So this correlation between the embodied energy and the carbon footprint really doesn't exist in Norway, because they're not burning any fossil fuels. Iceland's another example. They're 100% renewable with hydroelectric and geothermal sources. Again, there's no carbon footprint associated with the energy production. France is 75% nuclear. Again, another good example of where this relationship kind of breaks down. But really, for most of the world, we're still burning fossil fuels, hydrocarbons. The resulting product is CO2. Okay, I think I can skip the good housekeeping. We talked about this also in an earlier presentation. But basically, what this says is, if you want to know how much energy you're consuming in a manufacturing process, basically you simply have to look at how fast are you creating the part. And the faster you can create the part, the lower the energy on a per kilogram basis is. So this is sort of a specific energy. It's not the total energy. But the energy per kilogram of part produced drops significantly as I increase the build rate. Yeah, I showed this one last time too, where we can see where some of the various processes lie. Again, I'm a little confused why BED is so high. It should be lower, I would think. I assume that has to be powder-based DED, and the the wire base has to be further down the curve. But anyway, so we've already talked about that. Let me just to give you an impression of what the how energy analysis can look. I looked around. I couldn't find anything on an energy analysis for DED, but I did have one. Actually, this is work that I did with the guys at Nottingham in the UK some years ago. This was about 15 years ago, but it was with powder bed fusion and with nylon. So we looked at nylon powder bed fusion, and what we see is that basically the machine, we were working with a 3D Systems IQ machine, is it took about 4,500 watts to run the machine. So this is time in minutes. So it goes up to 1,000 minutes. So this is during the build. And so this is the energy that's basically coming through the plug to the machine. And so it's the total energy consumed, about 4,500 watts. So the question that we had is, well, where's that power going? How's it being dissipated? What is it being used for in the machine? And this is what we discovered from doing an energy analysis of the machine. Is that about a third of that energy is going to the chiller system to provide cooled water for the laser. Another 10% went to the laser system, so basically producing the laser spot, the laser beam was another 10%. So about half of the energy is associated with the laser. Again, that's not totally surprising. There's a heater system that took about 25% of the power. And that's, again, something that's sort of specific to powder bed fusion of polymers. Because for those of you that haven't worked those machines, there's a large plenum inside the machine, where basically there are feed cylinders, typically on both sides of a build chamber. And then it's maybe 1.5 meters by 1/2 meter by 1/2 meter. It's a fairly large space. That entire space is heated up to about 170 degrees centigrade, and it has to be held at that temperature for the duration of the build. And then not only that, but there are heaters associated with the feed cylinders, because we preheat the powder maybe to 140 degrees or so, and then the build area, there are typically radiant heaters that heat the build surface to, again, about 170 to 180 degrees centigrade. So it's basically a big oven that's operating during the build, and the build is so basically we have a lot of heat going in there, and we're producing a relatively small amount of part. So a full chamber build, might produce, I don't know, maybe 4 or 5 kilograms of part. And so you have all of that energy that's concentrated into 4 or 5 kilograms of part. So anyway, so we have that. Then the other stuff, so that's about a quarter of the energy. And the rest of it is sort of moving mechanisms around. The stepper motors for the piston control to move the feed cylinders and the build cylinder up and down respectively, roller drives, and then various other ancillary equipment, blowers, computer, and other things. So that's where the breakdown goes. Here's our sort of the summary. This was for nylon 12. With laser sintering, if we do a 15% fill, so basically if I have a chamber that is, say, maybe 1/8 of a cubic meter, what we're saying here is the normal fill would be about 15%. So 0.15 of that 1/8 of a cubic meter would actually result in parts. So we assume that we have sort of a reasonable build. We build that as material. It turns out that the energy per kilogram of part for nylon powder bed is 26.6 megajoules per kilogram. And you can see how that compares with some other manufacturing processes. Injection molding is about the same. Extrusion is much less. Machining is very low. That's assuming that we have a 50% loss of material to create a part. This is just for the process, for the manufacturing process. I also list the scrap rate. And I put for laser sintering, I put the scrap rate at about 0.3 because it turns out that with nylon you really can't reuse all of the material. And some material is actually lost to scrap. The powder bed fusion polymer people don't really make a big deal out of that, but that's the reality. That there is powder that winds up going to the landfill. Anyway, but however, if we include, the feedstock, it takes a certain amount of energy to create the feedstock, like the nylon in this case. And so if I scrap material, that also is a loss of energy. It's a waste because I paid a significant amount of energy to create that material, but then I'm throwing it away. So if we incorporate that effect into these based on the scrap, what we see is not surprisingly machining shoots way up because there's so much loss, but it actually comes in about the same as laser sintering. They're both fairly, fairly high energies. Injection molding goes up a little bit, extrusion just a little bit. But what we can see is that if we sort of look at these processes from an energy perspective, it turns out that machining has always gotten a bad rap because there's so much material loss. It turns out that at least for nylon laser sintering, it also is not particularly good. It's about the same as machining in terms of the energy loss. So there is one sort of repeating value here, and that is if you look at how much it costs, how much energy is consumed in producing nylon, it turns out it's like 116 to 128 megajoules per kilogram. So what this does is it sort of opens up the possibility to produce an environmentally advantageous technology. But what we do is we sort of widen our perspective from just looking at the manufacturing process itself to looking at what happens before the manufacturing process and what happens after the manufacturing process. So it's what in the engineering field referred to as sort of a total life cycle analysis of the part. So we look at the energy associated with producing feedstock, the energy associated with processing it, potential energy savings associated with service of that part, and then even at the very end, looking at things like recycling. Because if I can recycle the part, I'm not investing the energy to create a new one. I'm creating maybe a little bit of energy to convert it back to a new part. And again, repair is a classic example. So, but for this perspective, we're looking at it from the energy perspective. So we have that. So it turns out that there are some ways to produce low embodied energy feedstock, and with nylon, it's typically additives. So the question is, what materials are very simple to process into a proper feedstock? And it turns out that the approach that we can take is we can use these low embodied energy materials, which are typically wood and stone. We'll see a more complete list in a minute. But basically, we have wood and stone are the materials. And so what this would look like in a powder bed setting would be we could take stone and grind it, or wood and pulverize it, which is easy to do because in typical manufacturing for wood, it creates a lot of sawdust. And so we can start with the sawdust and process it into a material that would be appropriate for additive manufacturing. Typically, these would be mixed with a polymer. I'll show you some nylon and some polyester parts where we've done that. But that's the general approach. The other is we can use waste products. Again, we have sawdust, orange peel. There's a research group in Singapore taking durian husk, which I thought that was always fascinating. The durian husk and grinding it up to create additives for additive manufacturing, or it could be construction waste. The advantages of waste products is that the energy required to produce them is not tallied on our tally sheet. It's tallied on somebody else's tally sheet. So effectively, there's no energy involved in developing these materials. So I'm perhaps maybe grinding them or doing a little bit of modification to create the proper feedstock for it. But that's it. So here's another one. We can we can decrease additive manufacturing waste by, for example, developing recyclable feedstock. There have been some polyamides, some nylons that have been reputed to be, quote, infinitely recyclable, so that again you can continue to use the material over and over again without bad effects. But that's not something that it's not widespread. I'm not sure why. The other is we can do things like reducing the support structure. And this will be across the board for any material, including metals. Because if I can get rid of support structures, that in many cases can be a significant amount of energy embodied in creating that, and that's a waste product. All right, so let's look at here's this is shows the embodied energy in producing a certain feedstock. So, for example, and what I've shown here are sort of the common additive manufactured materials. So, for example, we start at the top. Titanium alloys take about looks like about 700 megajoules per kilogram. So I need about 700 megajoules of energy to create 1 kilogram of titanium. So it's very high. And coming down the list, we go not too far, we hit PEEK, polyether ketone, which is typically a powder bed fusion fuel feedstock. Then we get to the nickel-based superalloys, which have a lot of application space in additive, also very high. Then down to aluminum. The polyamide you see is running around 110, 120 megajoules per kilogram. The epoxies, which would be like the vat polymerization materials, are up there as well. ABS for extrusion is also quite high. Then we get down to stainless steel. Polylactic acid is a little bit lower. And again, keep in mind the y-axis is a logarithmic scale. So with polylactic acid, we're down to about 60 or 70 megajoules per kilogram. But if you really want to go low, I list down here at the bottom the ones that are really low, where we're talking, sort of 5 or 10 megajoules per kilogram of energy required to produce the part, and or less. And so what we have basically are some woods, and then some sort of ceramic type materials, concrete, and stone. So stone comes down, it's sort of a fraction of a megajoule per kilogram to produce. Because I guess it can simply be crushed and pulverized, and you're in business. So anyway, so the materials that we would look at for low embodied energy feedstocks would be these ones that are in green. But we can also, this is my one. I'm sorry. Yeah, again, this shows where they fit on the carbon footprint versus the energy of primary production. And again, it's the same kind of deal. It's a different looking plot. But what we see again are the common additive manufactured feedstocks. And again, there's down here at the bottom is where we would go looking if we were going to try and find a low embodied energy feedstock. This is the one that sort of separates wood from stone, and that's the amount of water usage. So it's how many liters of water do I need to create 1 kilogram of feedstock? And obviously, trees require water, and so what we see, if you look sort of up now, sort of in the middle of the plot there, on the left, you see some of the woods. So they're much less attractive. Of course, stone and the stones and the slate and the concrete, they require some water for processing, but not much. And so you can see that down there. They're down around 10 liters per kilogram, as opposed to, say, 1,000 liters per kilogram for water for wood. So we have, and so basically, sort of the end of the day, if we're based on this, if we're really going to try to go after a low embodied energy material, and one that was sustainable, thinking about water, then we would pick stone. And so that's where we're headed. So, but I've worked with wood and stone. So let me just show you. This is some work that I did. When was this? 2013. So I guess it's been about 12 years ago. I did some work with a Chinese university, actually in northeast China in Harbin, way up near the Russian border. Is on the other side, on the east side of Mongolia, is a city called Harbin. And the Northeast Forestry University is there, and so I had some collaborations with them because if there's one thing they have a lot of, they have a lot of wood, because that's the purpose of the university. So what we did in this case is we tried to make a wood plastic composite, and I want to just show you how this worked and what the issues were. The wood powder was mixed with plastic in a 1-to-2 ratio, 2 parts plastic, 1 part wood. And then there were a few other additives. But the wood powder was a variety of materials. We played with rice husk powder, with eucalyptus powder, and aspen powder. And plastic was PES, which I think is polyester sulfane or something like that, but also with nylon 12 material. So we were able to produce parts. This shows some parts. These are all sort of 10 to 15 centimeters across, and we were able to make parts that looked reasonably good with these feedstocks. But the issue is that adding the wood to the nylon just completely messed with the mechanical properties. So we see over here on this side, depending on what the laser power was for our composite, we got tensile strengths sort of from 1/2 up to about 3.5 megapascal of stress. And what you have to appreciate, just as kind of a rule of thumb, in order to be able to easily handle a material without it falling apart, you typically need about 5 megapascal. So these were very difficult materials to work with, even after processing. The Young's modulus is showed as well for a variety of input powers, to be around 200 or so at the peak. But for comparison purposes, though, we're talking 3.5, 4 megapascal. For DPES, that is for pure PES, which is what these materials were, the tensile strength is 90 megapascal. So we've been able to successfully drive the tensile strength from 90 megapascal down to 5, more or less. And the Young's modulus is around 250 gigapascal, and we've driven the Young's modulus to about 175 or more. So the sort of the takeaway from this is we can, with additive manufacturing, we can improve the sustainability by adding low embodied energy feedstocks. But the problem is that it really kills the mechanical properties, so which is a real problem. So moving on, this is stone. These are some examples of stone work with laser sintering. So in this case, we had nylon that we mixed with limestone. And so you see the micrograph over here with the arrows pointing to these little particles of limestone. Then we also have nylon. This is in the powder. We were able to produce parts that actually had reasonable strength. They were reasonably handleable. And the other thing that was kind of nice about them is they sort of had a nice feel to them. They sort of had that limestone kind of look, which was kind of desirable. It turns out limestone, it turned out that from Austin, about maybe a half-hour drive north of Austin, is an extremely large open-pit limestone quarry. And so we were able to go up. I just hop in the car, drive up there, and it turned out that they classified their limestone into various grades. Most of it was used for road paving, and it was in the form of pebbles in size. But the finest limestone powder that they actually had, that they put together, was about this size. We're talking sort of 10 to 30, 40 microns. which is great size for us. So we would go, they sell this stuff by the truckload, so we'd go and get, it'd be 2 or 3 kilograms. They just give it to us because it wasn't even worth their time to fill out the paperwork for us to buy it from them. So that was nice too. So we were able to bake the powder and then take it back to the university and run it. So this is the kind of thing that we see. Again, it's a really nice. It was nice parts. They also were better than the wood, but still quite frail. So they would break very easily. But they did have good detail and held together pretty nice. So here's some other examples on how we can get environmentally friendly feedstocks. And one is the one on the left is polymer powder that was produced using from castor heads. So you may be familiar with production of hydrocarbon fuels from agricultural products like corn. We produce ethanol that way. Well, this is sort of the similar kind of approach. It's producing polymer powder instead of fuel. And again, it comes from vegetable sources, from plant sources. And so this company, I guess Advanced Laser Materials, was producing those materials. Advanced Laser Materials actually it's a Texas company, and it was a spinoff out of my lab from about 2005. So it's nice to see that they're they're, again, as I mentioned, they're sort of a boutique feedstock supplier, and so they've gotten into this environmental game. On the other side is a stone sculpture from Desandera. And it's using, again, I think it's using stone waste and processing it to create parts. It looks like a fairly crude part. But anyway, there are some sustainable polymers that or waste converters for producing added manufacturing feedstock. Now I listed down here, UVX materials, plastic gap. It produces polymer filaments, frame it for material extrusion from waste. So we have that. So these are some of the ways basically that we can get towards low energy feedstock. In the metals game, there was, I can't remember what the company was, but there was a California company that associated Southern California, associated with aerospace, because for producing commercial aircraft, a lot of the structures are machined from raw plate, and there's a lot of chips produced. And this was a company that would work with the aircraft chips to use that as feedstock to create parts. And again, these were very large parts because the feedstock from the chips, of course, was very large particulate material. So that can be done as well. Okay, so another approach is to environmental friendliness or improving the sustainability of additive is instead of looking at feedstocks or the manufacturing process, is to basically say, is there something about additive manufacturing that can improve the service life of the part in a way that we save energy? And again, sort of the classic case is if I can create a part that goes into an automobile or that goes onto an aircraft structure, if I can save weight, it'll improve mileage, and that mileage means I have more gas left over, which means I've saved energy. And so it's basically lightweighting for transportation has been the historic argument that's made here. So having said that, turns out that the U.S. Environmental Protection Agency for automobiles, I found data that said that for if I could save 1 kilogram of weight on an automobile, then over the life of the vehicle, I would save 4 liters, about a gallon of fuel, which is not very much, frankly, right? But if you think, we have, if my Ford car. You know, if we save a kilogram of weight by using added manufactured parts, it means I say Ford gallons, but Ford produces like 10 million of these a year or some crazy thing, right? So I take that 4 liters and multiply it by the number of automobiles. It turns out you start to get significant numbers of them. And again, it's over the life of the vehicle, so you'd have to think, right, what, 5 to 7 years, maybe. So you know, to do the math. So you know, because of the large numbers of automobiles, you know, this can become significant. It's a little more direct with aircraft. With aircraft, the lifetime savings for fuel, again from the EPA, is that if I can save 1 kilogram of weight on a commercial aircraft, that over the life of the aircraft, we could get 5,800 liters of fuel savings. So this starts to become considerable. Granted, there's a lot fewer aircraft flying than there are automobiles running around. But having said that, it's still, you know, we're still talking the potential for some significant fuel savings. And so again, the advantage is you know, the advantage to additive is that with additive, we can create lightweighted parts perhaps much easier than by traditional manufacturing methods. You know, by using cellular or lattice structures, by using topology optimization, and we can carry that over and enjoy the benefits and the service life. So we have really these 3 areas. Actually, the 4th area I didn't really talk about very much. That's the recycling of the material. So those are the 4 areas that we look at when we do total life cycle analysis. And in additive, frankly, my experience is that additive looks a lot better when we do the total life cycle analysis than when we just look at the manufacturing section alone. Because again, I've seen energy analysis for powder bed fusion and for material extrusion, and neither one of them are very flattering when you're just looking at the energy involved or the energy consumption. Okay, well, I've got a few more slides here, and we'll have some time to do wrap up and some discussion here. So I wanted to mention a source for considering what are the issues with energy and sustainability. There's this rather dated document from 2009, the Roadmap for Additive Manufacturing, Identifying the Future of Freeform Processing. I think it's available online. Actually, somebody here at NIT Warrenville, I was talking, actually has a copy of it, which is great. I can't remember who it was, but we talked about that. It's this was generated with funding from the National Science Foundation and the Office of Naval Research in the United States. There were 3 of us that really organized and led it. I was sort of the first among equals. The second person was Megan Liu from Missouri University of Science and Technology, and the third was David Rosen, who's now at Singapore. But we sort of organized this, brought a bunch of people together for 3 or 4 days, and talked about essentially it was the question that was asked in a variety of areas was what research needs to be done to really enhance additive manufacturing in this area. And for I think really the first time in these types of studies, we actually looked at energy and sustainability, and we made sure that the people in the room, that there were representatives from that area who could wisely comment on the needs. This is sort of the executive summary of where the research needs in energy and sustainability are. One is, again, theoretical and practical cradle-to-grave life cycle inventory of AM materials. This is effectively total life cycle analysis. So we're going from when the material was formed to when the material dies or is recycled. So we, I guess I think I get the story right. At this meeting, we're talking about cradle to grave. Somebody made the analysis. They said, yes, if we take the part at the end of its life and throw it away, and it disappears that's like Christianity, but we recycle it's like Hinduism. So just to make the analysis. But anyway, charging ahead, we need design rules for sustainable processes. Basically, what are the things that are important in designing parts that have sustainable factors? Again, keep in mind that typically, if we go into environmentally friendly materials and feedstock, that the mechanical properties are almost definitely going to suffer. So we need those design rules for how to work with those parts. Life cycle value engineering model, I've already beat that, I think, well enough. Equitable indicators for measuring sustainability in additive manufacturing products and processes. These equability indicators, it's something that the environmental people use, and it has to do, it's fairly detailed analysis of the environmental impacts. So the equitable indicators, for example, an equitable indicator might include like what country you're in. So that there would be these indicators. So you'd look up Norway or you'd look up India to see what about the energy source. So it's those kinds of things that are very specific, so that you can build a reasonably accurate model for what the environmental impact is. And then finally, we have energy models, compare energy consumption and environmental performance between AM and traditional processes. So basically some work needs to be done to be able, we have the energy models in place for the traditional processes, but additive manufacturing is new, and those have not been developed. To the best of my knowledge, they still haven't been developed. So anyway, so that's that. Again, I think you can get this online still. Just go roadmap for additive manufacturing, 2009. Hopefully it will pop. Okay, I just have a few more slides here. So I want to just sort of conclude or summarize where we're at with the sustainability. Is first of all, additive has potential to make a positive impact on sustainability issues. I think that's really true. Second, increasing processing speed has a positive impact on energy consumption. This is the Gutowski plot. AM is most favorable when considering the material's total life cycle. Again, if you just look at the manufacturing piece of the entire event, my experience is that additive is not particularly, it doesn't shine very well in terms of environmental aspects. And then we can use recycled feedstock, low-embodied energy feedstock. It's desirable, but we have to have adequate performance. It has to be maintained. That will be the hard part of the effort. And then, of course, more research is needed to develop an improved picture of the positive role that AM can play on sustainability. So there's a lot of work that needs to be done in that area. So with that, I think I'm ready to move to, this is the last content slide. So this is sort of my picture of where we're headed, and looking at the big picture. That is that additive manufacturing, I think it continues to grow and diversify. We're still seeing that. The technology, I think, when we look at the metrics, it's, I think, reasonably fully recovered from the pandemic. The only area that I'm aware of where maybe we're still recovering is in the publications or the patent generation for additive, because there was a dip. And I don't know if it's a dip that's going to stay or a dip that's going to come back. The field is advancing on numerous fronts, incrementally into transformation. We see some exciting things happening like AI and other aspects popping in, but also there's a lot of really good work going on around the world that is pushing forward the application space for additive manufacturing. It's proven to be versatile and agile, continues to prove its value in a variety of application areas. So I think we're really at a point where, you know, additive manufacturing is really sort of in many respects, in many application areas, has actually proven itself. It's made its case, and so people are comfortable with using it. Now, that wasn't the case 30 years ago when it was a brand new process. As a matter of fact, I don't have to plot you. If you plot the meeting attendance at the SFF conference from 1990 to the present, from 1990 till about 1995, there was this big increase. The first meeting had about 45 people. By 2000, let's see, when was it? It slowly grew. By about 1995, 1996, it had grown to 200 people. But if you look at who those people were, they were largely industrial people. And what it was people from companies that had heard about this thing, and they were looking for a place where they could find and learn more. And what happened is they would come to the SFF to learn more about what this technology was. And then what happened from 1995 till about 2005 is there was a slow decrease because those industrial types found out what they needed to learn and they went away and didn't come back. So we actually had a decrease for about 10 years in the attendance. But again, it's the industrial, it's the industry people that were just coming to learn about it. I think we're sort of past that now, where industry knows what the technology is, and they're either using it or not. So yes, that's my point with the industry. You know, designers, you know, are finally confident, you know, employing technology for creation of structural parts and service applications. Again, we have 141 patents, standards out there to help define the practice to be able to facilitate commerce and additive manufacturing. It's sort of like Casio. It's, you know, the designers sort of know how to work with the material and where the shortfalls are. So that's a very good thing to be able to confidently design. Then we expect that environmental impacts will occupy a more prominent place in the nation. The international narrative, and will become increasingly postured to capitalize on the ecological benefits. Just now, I think in the last couple of years, the European Union has created a focus on environmental effects, and that's resulted in significant funding for research in that area. I think in the United States and under the current administration, that probably won't be happening for the next 3 years anyway. But at least, you know, in many of the responsible parts of the world, that, you know, environmental effects is starting to is sort of again having kind of a renaissance. So anyway, so for my final bottom line is, again, it's a versatile and broad technology. It's going to continue to grow and evolve with societal needs. You know, and certainly significant aspects of that are with the metal powder processes, with powder diffusion and with the wire powder-based DED. You know, they have their place in both in the AM world and in the manufacturing world, and I think they're going to continue to grow. They're going to continue to be important, and along the way, we'll be seeing some transformational changes. I'm not sure what they will be, but I think it's fair to say that they will be coming. So with that, I guess we have about 15 minutes left. So I'm at the end of the presentation. So again, I guess we can open it up for questions or anything you want to know. Really, I guess if you have questions really about anything related to additive, I think I'm now we can to do it.
Does the participants have any queries?
Sir, can you provide us Woolworths report?
Oh, yeah, the Woolworths report? Yeah, would you like it?
I'm unable to access it, sir.
The way you get, the question was, how do you get to the Woolworths report? The Woolworths report, I'm going to give you the long answer. It's about 700 or 800 pages. It's an annual report that Terry Wohlers I think he started around 1992 or 1993, and he produced it every year himself. He sold it to ASTM about 2 or 3 years ago, and ASTM has been publishing it, but still has the same flavor of the old Wohlers reports. So that's the introduction. But and by the way, it's a state of the industry for additive manufacturing. It's incredible. It's absolutely chock full of data that's extremely useful depending on where you're coming from. So for me as a researcher, the advantage is to be able to say, it's like, okay, I want to talk about how valuable. Suppose we want to talk about how well. I'll give you a real example. I want to know where are the DED machines in the world? The data that I presented all came out of the Wohlers report. So, or if I want to know what's going on in India in additive manufacturing, there's a section on a country section that deals country by country with what's going on within the countries. And there's a lot of investment stuff that I don't really deal with, but as I read those investment chapters, for someone that was going to be providing money potentially as venture capital, it would be absolutely invaluable. It's just where the money's all going, what it's going to, what it's going for. So anyway, so having said all that, now to answer your question, which is how you can get it, I think if you just Google up Wohlers Report 2025.
I tried that, sir, right now.
Oh, it didn't work?
But it is asking payment reports.
Oh, let's see. Yeah, well, you want to look at it. Oh, yeah, that's the difference, sir. I'm thinking about buying it. Yeah, you just want to look at it. Yeah, that's a harder question. I was just going to pop it up here. Let me catch up with you. So, Wohlers Report. This is what you saw, I guess. This is not Terry Wohlers. But it looks like, that's a promo. I was going to look for just the report. I guess I have to get past all this stuff. Is that what I need? Yeah, there's Terry. Yeah, I just want to go to the website. There you go. Yeah, there we are. Yeah, so it's there's a copy of the report. I was looking to see how much it costs.
Around $850.
How much is it?
$850.
$850. Yeah, that's not cheap, unfortunately. Yeah, so I think the 2025 is out now. As a matter of fact, I know it is because I've been quoting from it. Yeah, the answer is you have to buy it so you can access. I mean, that's unfortunately is the answer.
Yeah.
So, which is a real shame. But for example, I mean, what I would consider would be, I don't know how the dynamic works here within the university, but what I would do at my university, if I were there, is I would go to the libraries or go to my chairman and say, look, the university needs to have a copy of this because it's a valuable resource, but it's expensive. Try to get somebody else to pay for it. That's what I would do. But I don't know if you can find old copies, but the newest copies really are the best. I've been in kind of, I don't think I would buy it myself. I think I don't have 850 disposable dollars, but I wrote for him for a very long time. I do the research chapter, and I did for about 4 or 5 years. I did the future of additive, the final where it's headed chapter. But anyway, he basically, the long story short is he put me on his good list, and what I could do is I basically, they would just automatically give it to me, but I can ask them if they'd send me a copy. And they're generally pretty good about doing that, so I can get a copy. But I don't think that would work for you, unfortunately. I wish it would, but it doesn't. Yeah, but I highly recommend it. It's a fantastic course.
May I know what your current research work is?
I'm sorry.
What you're currently working on?
Me? Yeah, that's a good question. Yeah, what am I currently working on? In research, I'm currently working on nothing because I retired 2.5 years ago. So I've sort of ended going into the laboratory and doing things. Although, as I mentioned, I'm involved, with service type activity, So, but nothing in research. Yeah, the last student of mine, I sort of went full circle back to polymers. The last student that I had graduated about 4 years ago. Well, this was about 6 years ago now. It was trying to improve the consistency and the reliability of properties in nylon from powder bed fusion. It's a big problem because people will run nylon. One day they get 2% elongation, the next day they get 50%. It's widely varied. So I worked with a student to try to understand what was going on. I think we did a pretty reasonable job. But yeah, so I'm not doing anything now. It's great. It's fun. I don't have to worry about paying students or anything. I just sort of do my own thing.
Sir, in the past 1 hour session, all the slides that you have presented, that is actually my work I'm doing right now in fiber composites. So what would you suggest in which direction I should follow regarding this?
Yeah, with fiber, the directions would state the fiber processing. Yeah, I guess it depends on really what you want to look at. And if you want to look at basically machines to process the material, you want to look at feedstock creation, you want to look at mechanical properties or properties of the materials, depending on where you want to go, I think that would be the direction. And again, there's a small amount of composite work going on out there, but I'm not really, very well versed in what that is. If I were betting, I think like I mentioned earlier, if I were betting, I would bet you'll find aluminum silicon carbide because it's just such a popular metal making composite. Yeah, sure. Absolutely. Yeah, thank you.
In one of the classes, you have mentioned about the rare earth elements that are additive manufacturing. In one of the classes, you have briefly mentioned about the rare earth elements that are used in additive manufacturing. So, can you elaborate the scope of alloys with rare earth elements in additive manufacturing?
Functionally,
Yeah, I'm sorry, I kind of lost it. Layered
Rare earth element alloys.
rare materials.
Louder, please.
Yeah, I'm sorry. We're working on an answer for you.
Sir, he is asking about rare earth materials in additive manufacturing.
Rare earth materials.
Yes, spell it. How do we say it?
R-A-R-E.
Yeah, hang on. Yeah, sorry, this is all my issue here. Oh, rare earth. Okay, rare earth materials. Yeah, thanks. Yeah, sorry about that. Yeah, the rare earths. My experience with the rare earth materials is that it's they're used as alloys and they do a fantastic job of changing the microstructure in the metal processing so that we can avoid the factors that contribute to cracking during the process. So, for example, I think there's work going on here. I was talking with somebody about 7075 aluminum, which is a terrible material to fusion process. But by adding rare earths, I think it was rare earths, they were able to produce parts that they would not crack. That's the only application of rare earths that I'm familiar with. And I think for dealing with materials that that are not added, that cannot really be processed by additive, it's a fantastic way to sort of reheat those materials so that they can be processed. If that's where you're headed. But yeah, it's a wonderful thing. I think, you know, scandium and aluminum. You know, basically what the rares do is they serve as nucleation sites for grain growth on solidification. So it really facilitates the formation, sort of the destruction of the columnar type structures that generally tend to create porosity and cracks. Again, it destroys the dendritic structure too, which is also a source of porosity. So yeah, so it's great stuff. So, yeah.
Any queries? Professor, I have one more. What is the scenario of AIM in biomedical applications like implants,
The
AIM technologies,
which technologies?
like ITBM suppose?
Outer bed fusion. You want to know what the
Biomedical, like implants.
yeah. So
Biomedical.
yeah. Again, I'm sorry. Yeah, these two things just don't.
What is the applications in terms of biomedical with respect to additive manufacturing?
The applications?
Applications
Oh,
of
applications for wire
implant manufacturing.
implants.
Yeah.
Oh, manufacturing. Oh, the publication.
Implants manufacturing
Yeah.
with respect to additive
Oh, with respect to the high,
additive manufacturing.
the powder bed fusion
Yeah.
specifically. Yeah. Okay. Yeah. So I think the question, as I understand it, is, you know, what are the applications for powder bed fusion for implant manufacturing? Right. Yeah. And so it's the application space that I see is there are a number of different directions. I think the titanium and stainless steel and cobalt chrome, just the standard implant materials. I think for metal implants, I think powder bed is being used for all those materials, for all those applications. So like, you know, hip cups, you know, skull plates, you know, all the standard places. Another area that's probably the most popular powder bed fusion additive manufacturing metal, biometal application are dental coatings. I think they're cobalt chrome. They're like things for your teeth, and they're specifically designed. There are several companies producing apparently like thousands of these a day for patients. Again, they're all very customized, right? Built patient specific. They're very small parts, so they build very fast, and so it's. I think probably in terms of the material usage, that's probably the biggest application for anything in biomed. So we have those. Again, I don't know if maybe I discussed with somebody bone hard tissue scaffolds is also something that additive, the powder bed's been used for. I mean, we had the first hard tissue scaffolds that we built in Texas was in the mid-1990s. You know, and again, it's the standard grade materials. It's that hydroxyapatite material that they built with scaffolds. We didn't do it, but we contracted with a company to implant them in rabbits and see how the bone growth would occur, and they worked reasonably well. So that's another application space is building lattice materials for scaffolds. There's one other area, that is there are bone implants. I'm not bone implants. There are metal implants where they use the laser sintering, but it's not because of the geometric. It's not because it's a customized geometry for a specific patient. They build these parts by additive manufacturing, but in standard sizes. So I think it's like shoe sizes, right? Where the surgeon would just grab the one that they think will fit the best, and closest good enough. But the reason they do additive is because the rough surface that we get, which almost always is bad, and we want to improve it, like by hybrid machining, that rough surface is actually good or the implant because it's good for bone growth, ingrowth, to help hold the implant in place. So these would be the kinds of things they would like, like the hip replacements where they would nail the part down inside the bone cavity, for example.
Are they following any standards?
The which?
Like for implant manufacturing?
Yeah.
Any standards?
Oh, standards? That's a really good question. Are there standards for implant manufacturing? That's a really good question. I don't know. I don't recall seeing them, but again, there's 140 of them, so they may be out there. I know that they have standards on materials and processing that would probably have some impact on.
Will they implement in future regarding?
Sorry.
Will they implement in future?
Oh yeah, I think in the future. I think absolutely. Yeah, as a matter of fact, the reason I think there absolutely is because with additive manufacturing and metals, two of the big application space areas are aerospace and biomed, and I can tell you there's a ton of aerospace related standards out there. I know that for a fact, and so if they're not already there, they should be. We probably could just maybe search. I mean, I don't know if we can do it or not here easily, but just see what ASTM ISO biomedical additive manufacturers. Just see what's out there. Standards. We see what AI says, I guess. They look like they're doing the general ones. Yeah, so here we go. Yeah, so here's some that are popping up. 3456, how to reuse schema, kind of infusion for medical applications. 748, selecting appropriate biocompatibility test for metals and devices. This is aviation. But it looks like there's some, here's the quality assurance issue. So I guess there's at least one or two out there. But I think they should probably pop up fairly easily with the search. So, and again, I don't know what those are. And again, to sing the second verse of the song, the first verse dealt with the Wohlers report, in order you're not going to be able to find these for free online. You're going to have to pay for them. But fortunately, they're not $850 each. They're more like $40. So again, you have to fork over some money to get the full standard, unfortunately. So, yeah.
Thank you
Yeah.
very much.
Yeah.
We are closing this completely the 5 days program on this GIAN repair and remanufacturing parts with the direct edit deposition process. We'll be back into the same hall by 2:30. A quick MCQ test will be there. And then afterwards we'll go for the valid process. Okay. Thank you.
Good afternoon, everyone present here. It gives me immense pleasure and pride to welcome you all to the valedictory ceremony of the 5-day GIAN course on repair and remanufacturing of parts using directed energy deposition. We are gathered here today to mark the successful culmination of 5 insightful and engaging days of academic exchange, hands-on learning, and collaborative knowledge sharing. This course has truly been a remarkable academic endeavor, one that brought together experts, researchers, and participants from across the country under one roof. On behalf of the organizing team, I extend my heartfelt thanks to the Department of Mechanical Engineering, NIT Warangal, for their consistent support, meticulous coordination and commitment that has ensured the smooth conduct of this course. At this moment, I kindly request all our esteemed dignitaries to come forward and take their seats on the dais. We are deeply honored by the presence of the following distinguished guests. Professor S. Srinivasa Rao, Dean of International Relations and Alumni Affairs, NIT Warangal and Local GIAN Coordinator. Professor David Borrell, International Faculty from the University of Texas at Austin, USA. Professor Y. Ravi Kumar, Head of the Department of Mechanical Engineering, NIT Warangal. And Professor M. Manjaya, Course Coordinator, Department of Mechanical Engineering, NIT Warangal. We warmly welcome you all and thank you for gracing this valedictory session for your valuable presence. A special welcome goes out to all our enthusiastic participants who have joined us from various parts of India across Karnataka, Puducherry, Andhra Pradesh, Telangana and several other regions. Your active involvement, diverse perspectives and intellectual curiosity have enriched the learning environment throughout this course. The GIAN course officially began on 23rd June, Monday 2025, and over these 5 days, participants were immersed in a comprehensive exploration of repair and remanufacturing of parts using directed energy deposition, a field with immense industrial relevance and future potential. The sessions were thoughtfully structured and delivered by both national and international experts, creating an ideal blend of theory, practice, and futuristic insight. We are also proud to share that as a part of this course, we have successfully released a dedicated GIAN course book, a curated resource that captures the breadth and depth of the knowledge imparted. This publication stands as a testimony to the academic value this course has generated. Now, to commence the formal address, I now invite Professor M. Manjaya, our respected course coordinator, to share his thoughts and reflect on this journey of the GIAN course. Over to you, sir.
Thank you. Once again, the dignitaries on the dais and as well as my dear friends and as well as colleagues and also the participants. Very good afternoon to all of you. And first of all, I thank all the participants who have came from the different places and involved for the entire 5 days for this GIAN program. And hope you have got a lot of insights of the manufacturing process as well as the laser direct energy deposition process where and all we are using, especially with respect to the major applications and where globally additive manufacturing stands in the aspects of the machine development, in the medical aspects as well as in the repair aspects. And also some of the practical sessions we've gone through that in the laboratories, got some kind of hands-on experience on the additive manufacturing process, especially for the wire arc manufacturing, laser powder fusion, and the FDM technologies and all. And also one of the experts from the Simo factories from the Solaris had given a detailed understanding how we can do the numerical modeling of the additive manufacturing process and all. And also Professor David Borrell has given a lost his entire 40 years of experience he has given in the ideas where additive manufacturing and when he has started in the 1979 for his career of additive manufacturing process. We have got a lot of insights from his lecture sessions for the entire 5 days and hope you got take back to your home some of the research developments you are going to still continue in these research area of additive manufacturing with respect to this GIAN program and all. I thank you all for this participating in this 5 days program. Thank you very much.
Y. Ravi Kumar, Head of the Department of Mechanical Engineering, to address the gathering. Over to you, sir.
Respected Dean IRA, Mr. S. Srinivasa Rao, the foreign expert, Professor David Borrell, the coordinator of the course, Dr. Manjaya, and the participants, and the students. It's a very good afternoon. coming to the course, so I personally, I happen to be work in the same area, and it's my pleasure to listen one of the pitamahas of additive manufacturing, so which we can see his entire career of 40 years, which he has worked in this area, and it is a good opportunity for us, right? I hope, especially you people, like the participants, you are very lucky. In fact, personally, I am also feel very happy to listen his classical presentations, where he shared all of his experience, right? And yeah, I hope we want to listen from you. So yeah, all the best for your career. Thank you for the opportunity.
Thank you, sir, for your continued guidance and encouragement throughout this initiative. Moving forward, it is now my honor to invite Professor S. Srinivasa Rao, Dean, International Relations and Alumni Affairs and Local GIAN Coordinator, to deliver the valedictory address. Over to you, sir.
Good afternoon to all. Special thanks to the coordinator, both coordinators, David Burrell and M. Manjaya, for successfully completing this 5-day GIAN program. And I thank all the participants for showing interest to attend this 5-day GIAN course on repair and remanufacturing of the parts. So it is very much relevant to our country context during the inaugural address also I told. So we are moving towards Make in India and Made in India schemes, and this whatever knowledge you have acquired by attending this, definitely it will be useful for you to develop latest technologies in this domain area. And you have it is I'm very happy to know that the foreign expert has worked past 40 years in this additive manufacturing and manufacturing related areas. He might have shared a lot of his experience, expertise and exposure in this area, and you might have got a lot of knowledge in this manufacturing process. So all of you should further and further enhance the knowledge for developing the additive manufacturing related to any domain. Mainly nowadays this additive manufacturing is popular in medical equipment and medical field, but it is not only confined to that. So many different type of engines also can be manufactured with the help of additive manufacturing. So all of you know that additive manufacturing reduces the manufacturing process, and at the same time reliability of the equipment is going to increase because the number of welds, joints, etc. are going to reduce with help of additive manufacturing. And this, as per this title, also you have learned such type of contents. So all of you can use the techniques and technology whatever you have learned from the foreign expert David Burrell, and try to enhance and contribute something to the Make in India and the Made in India schemes, so that our country will become a manufacturing hub. And we all know that the manufacturing sector has to be further and further strengthened in India to meet our requirement, because we are world largest populated country. So we require so many areas we are supposed to become indigenous. So for that we are supposed to invent or develop some latest techniques to manufacture the various equipments which are required for us. So all of you might have acquired a lot of knowledge. My special thanks to David Burrell for showing interest and coordinating with Dr. Manjaya for submitting this this 5-day course. And finally it got approved by Government of India, and funds are released, and it was realized now. So there is a lot of 5 to 6 months rigorous work coordinators has to put. That is, you may not be knowing that it is a course is not started by printing the brochure and circulating. Before that, a lot of efforts are there from the both sides, particularly for foreign expert. Because the scheme is Government of India scheme, we all may show interest to propose a course. But our interest is not going to solve anything. Foreign experts, they have to show interest. They should observe our commitment levels and our knowledge levels and our expertise levels. Then only they will accept to coordinate with us. So my special thanks to Manjaya for approaching an appropriate person who is having vast experience in this manufacturing field. And I thank once again David Burrell for showing interest to come physically and interacting with all the participants here. And he is not only confined his stay here to teach only for 5 days during this program lectures. He had a lot of interaction with our MTech students, research scholars and department faculty. He made his visit very much fruitful, and NIT Warangal got a lot of benefit by physical presence of David Burrell. For that, I don't have any words to say. Many thanks to him, because he has involved in each and every part of this mechanical engineering related activities in the institute for the past 5 years. So thank you once again, sir, and I thank all the participants for coming all the way from your native places and staying here and observing our NIT Warangal campus. And you all know that it was established in 1959. From inception onwards, mechanical engineering department is there. It has its own significance from the inception onwards. So thank you, Ananda.
Thank you, sir, for your motivating address and continued support to initiatives like this. Now, I invite our distinguished international guest and speaker, Professor David Burrell from the University of Texas, Austin, to kindly address us and share his thoughts and feedback. Over to you, sir.
Thank you very much. To the platform and audience, it's been, first of all, I'd like to say it's been an absolute pleasure to be here this week in Central India and in Warangal specifically, to be able to share some thoughts and insights with you. It's been a delightful time, and certainly no small part of that has come from the excellent organization that was done by Professor GIAN and the others who were participating in organizing this event. It's certainly significant for this event was you, the participants in this week of talking about additive manufacturing and directed energy deposition. You know, we could not have this event without you, and I hope that it's been for you. It's been also a beneficial week, and that you will have learned some things that you will find useful in the future as you pursue your studies or your careers. Again, it's been a delightful cultural exchange for me this week, and certainly high on my list when talking with other people will be to have opportunities to share about my experiences here at the National Institute of Technology, Warangal. So again, congratulations, and thank you very much to everyone for a wonderful event.
Thank you so much, sir. Your presence and sessions have added tremendous value to this course. We would also like to acknowledge and extend our sincere thanks to IIT Hyderabad, the Nodal Institute for GIAN courses, for their patronage and sponsorship. Their contribution has been instrumental in making this program at NIT Warangal a reality. Before we proceed to the certificate distribution, we would like to hear from our participants. I warmly invite anyone who would like to voluntarily come forward and share their reflections or feedback about the course, your learnings, or your overall experience over these past 5 days.
Good afternoon to all. I'm Jay Kathir from SRM University, all the way from Chennai. So really we are very grateful to and the people who are organized here, head of the department and all. One thing I was telling about is Professor Ramalya and Professor Boril also. Even though I am working in the area of computational mechanics, we always speak that manufacturing process and verifying all those things. So, but every time it will be question mark, either during my 10-15 years back, my viva for my PhD work, and also when my scholars are presenting their work, the people will be asking that what will be that manufacturing feasibility. So, to be frank, I was managing the answer. So I know that personally that was not a correct answer. I hope here I got that. Even Professor mentioned in the last slide that research needed. So one topic theoretical to practical. So I think now we got that. And I'm very grateful to Professor David Borel. Vast experience, so many things I learned. As a research person, I learned many things about this, and also being a teacher, really, I told him very first day itself, really I was enjoying looking at his body language, even the day 1 to the last day, with more than 100% smile face, and not showing that any tiredness even in this age. Even I could imagine that in this 1979 he completed his PhD. That was year I born. So my my age is his experience. So physically how much he would experience, but he didn't show that. That is really overwhelming experience to look at that as a teacher. And really I'm very thankful to organizing people also, to providing such a wonderful campus and arranging all those things. Apart from organizers, we are very grateful to the participant volunteers. Really, we reached here Sunday morning itself, just to be made a call. One of the volunteers, Suresh, came here. He has given that immense support. Really, we never forget that. Even we organized some of the courses like that, but this accommodation, taking care of that accommodation, all those things, and food, and really it's wonderful, and thankful to all. Thank you.
Thank you so much, sir, for your valuable feedback. Any other participants who would voluntarily come up to share your feedback experiences of this 5 days? Can please. Now we come to the most awaited segment of the program, the certificate distribution ceremony. I request Professor S. Srinivasa Rao, Professor David Borel, and Professor Y. Ravi Kumar, and course coordinator Professor M. Manjaya to kindly distribute the certificates to our participants. I call upon participants one by one. Please come forward to collect the certificates. First, I would like to call Mr. Vasant M. Mr. Vasant M. from the Central University of Karnataka, Kalaburgi. Mr. K. Chandrajay from Methodist College of Engineering and Technology, Hyderabad. Dr. J. Karthikeyan PV from SRM Institute of Science and Technology, Chennai. Dr. Rajashekaran Tangaraju from SRM Institute of Technology, Science and Technology, Chennai. Mr. Rais Ahmad from Anna University. Dr. Murthy BRN from Manipal Institute of Technology, Manipal. Dr. Satish Rao U from Manipal Institute of Technology, Manipal. Mr. Sai Chaitanya from C.R. Reddy College of Engineering. Mr. Vadla Avinash from B.V. Raju Institute of Technology, Narsapur. Mr. M. Venkat Reddy from B.V. Raju Institute of Technology, Narsapur. Mr. G.V. Ashwit Kumar from B.V. Raju Institute of Technology, Narsapur. Mr. G. Vinay Kumar from B.V. Raju Institute of Technology, Narsapur. Mr. Rohan from SR University, Warangal. Ms. Ruksar Begum from SR University, Warangal. Mr. Shivam Singh from SRM University, Andhra Pradesh. Mr. Sai Dinesh from VNR Vijnana Jyoti Institute of Engineering and Technology, Hyderabad. Ms. Ambir Sindhuja from VNR Vijnana Jyoti Institute of Engineering and Technology, Hyderabad. Mr. Madhu Mohit from B.V. Raju Institute of Technology, Narsapur. Mr. Rama Karthik from National Institute of Technology, Andhra Pradesh. Mr. Venkataratnam P from Lucky Reddy Bali Reddy College of Engineering. Ms. Maheshwari Mutyala from VNR Vijnana Jyoti Institute of Engineering and Technology, Hyderabad. Mr. Ratwat Anil from VNR Vijnana Jyoti Institute of Engineering and Technology. Mr. Prasad Sopari from VNR Jyoti Institute of Engineering and Technology, Hyderabad. Mr. Galipalli Sai Rutvik from CVR College of Engineering. Mr. P. Harichandan from CVR College of Engineering. Mr. M. Varshit Raj from CVR College of Engineering. Dr. Gururaj Bolar from Manipal Institute of Technology, Manipal. Mr. Gottipati Dheeraj Sai from VNR Vijnana Jyoti Institute of Engineering and Technology, Hyderabad. Mr. Anil Kumar Maheshwaran from National Institute of Technology, Warangal. Thank you, everyone. As we conclude this enriching academic journey, I would like to extend my heartfelt thanks to Director Professor Vidyadhar Subudhi for his constant support and encouragement, and everyone who have made this event a grand success. The esteemed dignitaries on stage, the dedicated faculty members and the organizing team behind the scenes, and most importantly, the vibrant group of participants who have come across India. This GIAN course has not only contributed to the professional growth of all involved, but also foster the lasting academic connections. Let us carry forward the insights gained here into our future research, teaching and practice. Thank you one and all for being a part of this great academic journey. I now request everyone to please rise for the national anthem.
भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जगति तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जय गण मंगल नायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Thank you one and all. Please be seated. Thank you all once again for your presence, participation and valuable contributions. Before we end the session, I would request all our participants to come forward near the dais for a group photograph.
Ready, sir? Sir, ready? Sir, wait. Play program. Wait.
Thank you so much everyone. Wishing you continued success and safe travels.